if we look, we will stop now talking about indirect formulation. We'll talk about the direct formulation. Okay, we'll give idea or essence about the direct boundary integral equation, how to formulate our direct integral equation in elasticity. Okay, we will use BEM reciprocal theory. We'll use BEM reciprocal theory. So formulating direct integral equation in elasticity. I know I'm talking about a lot of stuff like jump terms, Cauchy principal value, or all of this. We will cover all of this in the coming lectures. We need time to build up the knowledge of the boundary. For example, if I have my problem here, something like wall like this, with our domain gamma of y, any point here y. When y move on the boundary, we'll give it the name x. So we'll have here u1 of x, and we'll have u2 of x. This is, I'm interested in these two value of this. And we have here tractions, forces or something like that here. And this is gamma. Okay, so I am in the infinite domain. So this is the first. This is the first problem. This is the first problem, problem number 1. The second problem is infinite domain, totally infinite domain. I'm going to put the shape of my problem here, like what we did in the indirect form. And I can choose, for example, here is a point x. I can choose any point here called xi. Okay? And I have two cases. For each xi, I can write for each xi. Remember, before we place the sources and we compute the superposition of these sources at a certain field point. But now, for each source xi, for each source xi, I have two cases. The first case, when I have the load in this direction. So I have the load in this, I will put 1 kilonewton or 1 ton or 1 anything, 1 pulse here. Once I have this pulse, I will have displacement and tractions at every point. So here, this will give me displacement in this direction and displacement in this direction. The name of the displacement here is the fundamental solution between the point xi. For example, this is xi1. Here for each xi1 and the point x. And the direction of load and xi in the direction 1, and I'm computing in the direction 1. Here is the fundamental solution between the point xi1 and point x, the direction of the load at x1, and the computing and the second direction 2. Okay, I have also tractions. I have also here tractions. So I have here traction in this direction and I have traction in this direction. So I have traction in this direction and I have traction in this direction. Between the point xi1 and point x, and this is also between point xi1 and the point x. The direction of the load here is 1, and I'm computing in the direction x1, and here is the direction of the load is the same 1, and I'm computing in the direction 2. And this is the second problem. If you remember BEM reciprocal theory, it gives me u at the state 1 times the traction at the state 2 equal to the displacement at the state 2 times the traction at the state 1. So we'll write here what we have here directly. Let us see the displacement at the state 1. Where is the displacement at the state 1? We have u1 of point X. And we have U1, U2 at point X. So plus here. Okay? Where is the traction at state 2 in this direction? So we have T11 here and we have T12 here. So we have T11 of xi1 and x. I'm giving T asterisk or something like that, like a fundamental problem. Let us do it on the figure with T asterisk also. And here I have T12 at point xi1 and x. Okay? Still, do I have another tractions or forces at xi2? Yes, I have this load. I have this load here, 1 ton. So I have this load here, 1 ton. So I have to add here plus here 1 ton, the 1 ton here at xi, and I have to multiply it by u at point xi. I have to multiply u at point xi. This xi could be outside the problem or could be inside the problem. It's not a problem at all. Okay? Coming back to this equation, this is the equal sign. This is the equal sign. Where is the displacement at the second state? The displacement at the second state is U11 and U12 here. So I'm going to write here U11 between xi1 and point x asterisk and plus U12 at point xi1 and point x. Where is the traction at the first case here? Here also I have T1 of x and I have T2 of x. Maybe in this shape of the problem, we have T1 equals 0 and T2 equals 0, but I could have a force here, a concentrated force or something. It's not a concentrated force. It is distributed traction on the boundary. So here I have to multiply by T1 of point x and I have to multiply by T2 at point x in general case. Okay? So this is better reciprocal same. But this is only for one boundary point x. So what I need here, in this area, I need to integrate on all boundary points of x. The same here, I need to integrate here on all boundary points of x. If I have domain load, here I have another. For example, here I have u asterisk here of 1 of xi1 and the point y. If I have domain load here, if I have domain load at point y, I have domain load in this direction B1 and in this direction B2, distributed domain load in this area. Okay, and this is point y. Okay, so I have here u asterisk 1, 2 of xi1 and y, and I have to multiply by B1 of y, and I have to multiply by B2 of y, plus, and I have to compute the domain integral over y. If we write this equation in general case, so we have direct u of xi, so we will have u of xi multiplied by 1 times u of xi, plus integral over gamma of x, t alpha beta of xi and x multiplied by u beta of x equal integral over boundary of x u asterisk, and this is asterisk, alpha beta of xi and x t alpha t beta, this is x t beta of x plus integral over the domain of y u asterisk alpha beta of xi. Now of xi, remember this is xi, is not like in the indirect case. In the indirect case you will see the field point of y times b of y, and this is b beta. And this is a direct integral equation. Of course, if xi is external point, you will have this term is 0. If xi is internal point, you will have this term is 1. If we have xi on the boundary, you will have it 1/2 xi. If it is smooth boundary like no kink or no corner or something like that. Next lecture, we'll talk exactly about how to get this 1/2.